Team, welcome back. Okay, now we're talking about mirrors and lenses. So, when it comes to these mirrors, let's focus first on mirrors. Mirrors are, especially when they're curved, they can make things either larger or smaller. And we specifically in this physics, we have two. We have concave and convex mirrors. When it comes to concave mirrors, the mirror has its reflected on inner side of the sphere, this side right here, right, the inner side of the sphere, and we call it a sphere because if this is a circle right here, the concave mirror would be this little part right here. So therefore, it has a radius. We can identify with a radius. And it will be essential later on because it does have a radius. The focal point is equal to the radius over 2, like you will see on the PRC equation. So the focal point is equal to the radius over 2. Now, then we have the convex mirror, and this mirror is reflecting the surface on the outer side of the sphere. But if that's the case, if rays are coming in for the concave, right here, right? Then the focal point is right here, which is perfect. But for the convex mirrors, the focal point is over here. Therefore, when rays hit it over here, to get to that focal point, it's going to have to converge somehow over the other side. But we'll discuss it a little bit more in the comings in this lesson. Okay, so looking at this one, these two things. One is for the concave, and the other one is for the convex. For this one, it is the concave. In this situation, the focal point, it has its rays reflected so that it converges at one point in this location right here. Okay? Now for the convex, the focal point is different because there are no real rays passing through it, like I mentioned in this one. Okay? So the rays are actually, they're still converging, but they are imaginary. They are virtual rays. So let's talk a little bit about the equation. So this equation right here is used for both mirrors and lenses. So I'm not going to talk about it in the next session for the lenses too much. Remember what I said about the focal point? So the focal point is just the radius of the circle, the center, not the radius of basically, as I mentioned before, let me just, so you're not confused. So if this is a sphere, this is the concave mirror, and this is the center, and this is the radius. Okay, and the focal point is right in between the radius. All right. Then we have the magnification. So if you know the distances or the height of the image of the object, you can solve for the magnification, which describes the image in terms of the object. All right, one last thing. Well, before we start heading into problems. In physics, we identify the mirror as convex or concave depending on the location of the object. So notice here the object is right here, but the mirror is facing away from it, like this. Look at the bend. That means that it is a convex mirror. Whereas in this, when these spikes right here are facing the object, it means that it is a concave mirror. All right, this is to simplify things further. This is for the ray tracing rules because we didn't touch a lot on it, but it is extremely important for us to identify the ray tracing. So ray tracing helps us to determine the location of the image formed on the mirror. And there are certain things, there's certain regs that it goes through, and these are the three regs that it goes through for the mirror. So I'm going to ask you not to worry about this, because if you notice on your course website, it says the 3-ray diagram. So you only need 3 rays. Okay, I know some of you asked like, hey, if you have 2, would that suffice? You will be able to find your image with just 2. I can guarantee you that. But if you want full credit on required problems or exams, you're gonna have to do it the way that the course website asks you. It's like, hey, 3-way diagram. So we're looking at three rays. So the first one, let's read it together. A ray traveling parallel to the optical axis of the spherical mirror is reflected a line that goes through the focal point of the mirror. Okay, so looking first at the actual concave. This is a concave mirror. The first one says that its optical axis is reflected along the line that goes through the focal point. So it goes straight, hits the mirror, and then goes straight to the focal point. It's traveling parallel at first. It's traveling parallel at first through the next to the of the optical axis, and this is the optical axis right here. This is the optical axis right here, and then it hits the focal point. Then the second ray is traveling along a line that goes through the focal point of a spherical mirror, and is reflected along a line parallel to the optical axis. So basically it says, hey, from the object, go straight to the focal point. Like what we're seeing in the red line right here. Okay, from the object, go straight to the focal point. But once it hits the mirror, you are going parallel from the optical axis. Okay, parallel from the optical axis. All right, so just with those two, you're already able to identify the image. But we need one more, and that's the ray traveling along the line that goes through the center of the curvature of the spherical mirror. The center of the curvature of the spherical mirror is reflected back along the same line. So the center is located right here. So it's going straight from the center. It's going straight from the object to the center, and then it's reflected right back, as you can see with the arrows. Okay, so right there, since it's going straight from the center, from the object to the center, to the mirror, and then right back, we can identify our image. Now for this one, it's a little bit more difficult because we're dealing now with imaginary lines. But bear with me. So let's go first for the first line. The first line. It goes parallel just like it says, like, hey, go parallel of the optical axis and then go through the focal point. But because it is a mirror, you actually have to go to the focal point with imaginary lines, virtual lines, like it's doing right here. Okay? And the actual light ray, the real light ray is actually bounced like this. Okay. Then a ray traveling along the focal point. So now you go straight to the focal point, but it says once you hit the mirror, it bounces back and you have to do it in a parallel. So this is why it goes straight to the focal point, but in actuality, in this point right here, it bounces back. So really, this is just helping you guide to center your line. But what you really want is that bouncing. Once it hits the mirror, it bounces. It is an optical, and then the virtual line is created parallel to the optical axis. Parallel to the optical axis. And then finally, it says, like, for the third ray, travel along the line that goes to the center of the curvature. Just straight line. It bounces back It bounces back, but there is still the imaginary line, the virtual line, that goes straight to the center, creating the image right there. Okay, so if it is confusing, don't worry, because we're going to be doing a couple more problems on this. So I'm going to bring this right here. I'm going to close the gap, make sure that this is clean. All right. I'm going to bring this here, and we're going to do this together. So let's first, I'm really moved out. Let's first write down the rays that we're going to use. So for ray 1, let's do ray 1. It is parallel, then focal. So that's how we're going to identify ray 1. Parallel, then focal. Then let's change to green. Ray 2 is going from focal, hits the mirror, then parallel. Then finally, let's go to the last ray, ray 3. And ray 3 goes from the object to the center C. Okay? All right, so doing this together, let's change to red. We go from parallel, the optical axis. It hits the mirror. Right after it hits the mirror, it goes down to the focal point. Now notice where the focal point is. Since the focal point is next to the object, and noticing also how the direction of the mirror is, this is a concave mirror. All right? And because the focal point is also next to the object and it is a mirror, this more likely will be a real image. Okay. So we passed it. We went through the focal point. Fantastic. Let's continue on. And then make it a little bit bigger. Now let's go to the second ray. The second ray says, hey, this time around, let's go straight to the focal. And then once we hit the mirror, ooh, I wish it was a line. Once we hit the mirror, we go parallel. So we hit the mirror, we go parallel. Ooh, man. You know, like sometimes I wish he would just give me a straight line. Here we go. Straight line. With just this, we can already identify our image. But the third ray asks us, hey, you have to go through the center. Notice that you're not hitting the mirror in this situation. You just have to go through the center. So you go straight down towards the center, from the object to the center, and voila. You have the 3 points of contact, and you have your image. And it is a real image, right? Because it is using real rays, and it is inverted. And is it larger or smaller? It is larger, at least from what I can tell from my diagram. All right. Now, let's go to the second one. This one is a little bit different. Notice the mirror. This one is going like away from the object, meaning it is a convex mirror. So we circle it. It is a convex mirror, and we start doing our awesome rays. Okay, so let's start with ray. It says, okay, so go from the parallel. We're going from the parallel, and right from the parallel, we're going straight to the focal point. So, unfortunately, let me say, okay, here we go. The focal point, here we go. Boom. And there is a light that is reflected. The light that is reflected but we have our focal point. Okay, that's the first one. Now let's go to the second one. Our second one says, hey, you have to go from the focal, then parallel. So we go focal, and this is a little bit tricky, is we're doing it in, and I'm doing it in this. Okay, so focal, and I'm trying to align it. Okay, so right here, right? So I align it right there. But remember, what really is going through here is not actually that. You hit the wall, and right after you hit the wall, it bounces back in a parallel fashion on the optical axis. What is passing through in the imaginary zone is the parallel ray. Okay? We can already tell this is where the image is going to be at. And then finally, we draw our line from the object to the center. Okay. All right, from the object to the center. Now, correctly speaking, you have to do like an imaginary, oh my goodness. Let me put it a little bit, okay. Imaginary lines for it, but this is, we have identified where our image is at. So our image is actually virtual, and it is not inverted, but it is smaller than our object. All right, so I am gonna leave it at that. You can do this one. You can do this one now that I taught you how to do these two, hopefully. Remembering these things, the 3 rays. And I'm gonna do a problem. Now this problem is simple. This problem is for a convex security mirror. I'm just trying to show you that it does not matter whether it's convex, lens, concave. The same rule applies when it comes to this equation. Okay? So we're given the distance of the object, which is 3 meters, and we're given the magnification of the convex, which is 0.250. So A, since we need to find that where is the image, and we have the magnification, and we also have the distance of the object, we can find the distance of the image, which is 0.75 meters. We now have to find the focal length. So now we have the distance of the image and the distance of the object. All we have to use is the equation for the distance of the image equation or the mirror equation, and solve for the focal point. And it is 1 meter, negative 1 meter away from the mirror. And finally, for the curvature, since we have the focal point, and that equals radius over 2, the radius of the curvature is actually radius 2.0 meters. And that does it for the section on mirrors specifically. I have another section just focus on lenses. All right, thank you.